So this one was like the hardest for me to understand when I was in Cal 2 back in the day. But once you see it, it's not too bad. Drawing a picture helps me figure out what's going on. So I'm gonna give you the theory, then I'll draw you an informal picture that explains the idea. Okay. So here's the theorem. Direct comparison test. So let zero, or let a n be between 0 and b sub n, but not equal to 0, just between there. For one second. For all n. This paper. One second. All right, let me write that again. For all n. Okay, so number one. If the series b sub n, as of course as n goes to infinity, from 1 to infinity, converges then the series a sub n also converges. Okay. Number two. If the series n equal 1 to infinity of a sub n diverges, then the series b sub n also diverges. Like that pen's a little light. So this is the requirement. So basically what you do is you have one series and you compare it. You'll have a question, right? They'll give you a series and they'll ask you, does this converge or diverge? Um, you'll pick a series that you know converges or you know diverges. And depending if it's less than or equal to or whatever, then you'll have some information. So I'm going to draw you a picture so you can understand it if you don't already. So basically, what this is saying, this Bn is bigger, right? So if the big one converges, then the one that's smaller than Bn should also converge. So basically what you're going to picture, this is a number one picture here. Trying to visualize what's happening with number one. So basically you have a series, kind of, let's just picture you're adding a bunch of stuff and eventually it converges, right, to some point. This is not exactly what's happening, but this is how I want you to visualize it. And you have no idea what it does, but you know it's less than Bn. So since this one converges somewhere, then this has to also converge. That is what number one is saying. So since An is less than Bn, this will happen. Does that make sense? Okay, so now let's do it the other way, if that makes sense. So if you know something diverges, let's say the small one diverges. Let's say that that's Bn. Then, sorry, An. An is a small one. Then, if the small one's divergent and the big one's up here somewhere, then it must also diverge. So basically, what we're saying here is, you know what one of them is doing, so you'll make an assumption of the other based on this theorem. Okay. And you're the one that will have to choose the Bn to compare to. It's won't be given to you. So let's do an example. Let's do this pen works. Let's stick with the purple. Determine the convergence or divergence of the series here. All right. So what we're going to do is compare this. So compare this to a series that we will choose. 1/3n. Okay. So this is a geometric series that we talked about in 9.2, I believe. So this one is bigger than this one, right? Because you have a +2. You see that? But first we have to figure out what the one I'm choosing, right? We need to figure out what it's doing. So we'll call this B sub n, I guess. One moment. Okay. So since the series n equals to 1 to infinity, 1/3n is geometric, and r is equal to 1/3, then the series converges. So now that we know that this converges, then I need this guy to be less than bigger than an. That's what we need. So let's do that on the next page here. So we're using number 1 of theorem 9.12. Let's look at it like this. 3 to the n plus 2 is bigger than 3 to the n, correct? Before we do that, you agree that 2 is less than 3. If we take the reciprocal of both of these, you see that 1/2 is now bigger than 1/3, correct? Which means that if I take the reciprocal of this would be smaller than this. So let a sub n equal to 1/3n plus 2, and bn equal to 1/3n. since A sub n is less than B sub n, and B sub n converges, or sorry, I should say, and the series of B sub n converges, then so does the series of A sub n. Does that idea make sense? We applied the first part of theorem 9.12. Is there any questions on the first example? So usually a good guess for Bn is a P series if you can show that it's bigger when you're doing a direct comparison. A P series or a geometric is usually a good choice, but only if you can show that it is indeed greater than. Okay. So let's do another one. Example 2. Use the direct comparison test to determine the convergence or divergence Okay. So here is the series. So the trick to this is, number one, deciding what is a good B sub n to choose. Since we have a power up here, I'm going to choose a B sub n to be 7 over 6 to the n, which is the same as, let me move this a little bit. Okay. Okay. So first thing we got to show, the first thing you got to do is choose a BN. Second thing you need to do is figure out if this is converging or diverging. If it converges, then it needs to be bigger than the original question. If this diverges, then it needs to be smaller than this. Otherwise, it will not help you. Does that make sense? Just think back. If you ever get confused or just dyslexic like I do, just think back to that weird chart I drew. Even though it's not legit math, that drawing helps me conceptualize the idea. So this is another geometric. 7/6 is bigger than 1. So if this is a series, then it will diverge. Let's see. Oops. Sorry, I screwed up. This should be an 8. All right. 1 moment. All right. All right, so this is less than 1. So when it was 6, it was diverging, but now it's going to converge. But let's put that in English real quick. So the series of B sub n here is a geometric series where r is less than 1. R is equal to the 7/8, according to the geometry examples we did last time. 7/8 is less than 1. Therefore, the series of B sub n converges. So since we know Bn series converges, then it needs to be bigger than this guy. Because if it is, then this one will also converge. So let's prove it to ourselves. All right, so I know that this for sure is bigger than this, right? I also know that this is smaller than this. Adding that 7n on top doesn't change anything, does it? It's still smaller. See what I mean? So since a sub n is less than b sub n, and the series of b sub n converges, then the series of a sub n also converges. Any questions in example 2? Do you see the logic here? Okay. All right, so let's move on to another test. So that was the direct comparison. This next one is the limit comparison. This is a lot easier to use because you don't have to worry about which one's bigger or whatever. You just have to look at the limit. This is called limit comparison. So if a sub n is greater than 0, b sub n is greater than 0, and the limit as n approaches infinity of an over bn is equal to L, where L is finite and positive, then the series a sub n and the series b sub n either both converge or diverge. So all you do is you choose the b sub n yourself, divide the original question an and bn, you look at the sequence part of your series, take the limit, and if it's positive and an actual number, then they will both converge or diverge. So you have to know what bn is doing. So for example, determine the convergence or divergence of n times 2 to the n over 4n cubed plus 1. Okay. So I'm going to compare it to, let's see here. Let's let Bn be the piece without the plus one. All right, so just ignore this piece. Notice how this will reduce into 2 to the n over 4n squared, right? So now divide an. An's already given to us, right? An is always the piece of the original question, the series part, the sequence of the series. So the limit of an over bn as n approaches infinity is equal to the limit as n approaches infinity of the an part divided by the bn part. So I'm going to just put it over here so it's neater. To the n over 4n squared, which will give us the limit as n approaches infinity of this first piece times the reciprocal, right? When you divide fractions, you take the reciprocal. And now let's start to reduce and cancel things. So the two n's will be gone. This will end up being the limit of 4n cubed, right? N times that there, n squared, over 4n cubed plus 1. So take this limit. It will be equal to 4 over 4, which is equal to 1. So since the limit as n goes to infinity of an over bn is finite / positive, and well, hold up a second. Yeah, we'll do that in a second. Then both series, man and bn, converge or diverge. So now we just need to check what the heck is the series of bn doing? Because once we know what that's doing, all right, so Let's check the series. 2 to the n over 4n squared. The first thing we should do is take the limit of the sequence. If this limit is not zero, then it diverges, which will then mean an also diverges. To check if this diverges, so far we have many tools, right? We got geometric, we got the nth term test or limit, we got the comparison test, and of course limit comparison, but we wouldn't do a limit now because we're doing the limit right now. So let's do the one I told you that you should always do first, is take the limit of the sequence, make sure it's zero, and then do another test. I have not been doing that. But if you were to take a limit here, it probably would not be zero. So that would show you it diverges, but we're practicing the limit comparison test, so let's not worry about that. So you take the limit of the sequence in order to do the nth term test. And you can't straight up take the limit. You get an indeterminate form, so you can do L'Hopital's from Cal 1. So take the derivative of the top, derivative of the bottom. That's going to give us, what is that? Derivative of this guy, it's a special rule. Thing's going to be itself times ln 2 to the n. Bottom will be 8n. This will then be infinite. Therefore, the series of Bn diverges. This means therefore, some math symbols, 3 dots. Okay. So since this diverges, An diverges. That's what we wanted to show. So since the series of Bn diverges, then the series of An also diverges. Is there any question on example 3? You guys cool on number 3 then, for limit comparison? Okay. Let's do one more limit comparison just to be safe. Okay. So the trick here, well, first thing we're gonna do, right? I haven't been showing the procedure. So first thing is check if the limit of the sequence is equal to 0. If it's not 0, then it diverges and we're done. We don't have to do any other tests. If it is in fact 0, then we start doing the other tests. I was a little focused on how the tests work, but let's start doing the procedure here. So the limit of the square root n over n squared plus 1 as n goes to infinity, that would equal to 0. One second. Okay, since the limit is 0, we must do another test. It tells us nothing. If this limit was anything else, it tells us that it's divergent. So let's do the limit comparison. Since that's what we're practicing, let's do that. So a sub n is equal to this. The trick is choosing what the heck is bn. So bn, we'll say, is going to be this other piece without that 1. It's usually a good guess. This will reduce, though, right? To, what is that? 1, 2 minus a half, 3 halves, right? N over 3 halves. There we go. So take the limit. I'm going to use this one during the actual cancellation, but just remember that it's this, technically. Okay, so here we go. So the limit of an over bn would be equal to the limit as n approaches infinity of this guy divided by this guy. I'm only using this one because I can cancel the square roots. I should technically use the reduced, but this is kind of nicer, less work. So that cancels, giving us n squared over n squared plus 1. That limit will be equal to 1. Right? So since the limit of an over bn is equal to 1, then the series shoot, give me one moment. the series AN and the series BN. So since the limit is equal to 1, then the series AN and BN both converge or diverge. So we just need to figure out what the heck is BN doing. Then we will know what AN is doing. So we're going to use this one to examine. We're going to examine this guy here instead of that one. The series as n goes to infinity. Sorry. Then it goes from 1 to infinity. Is a convergent P series, right? See how the P is greater than 1? Since P is equal to 3/2, which is greater than 1, this means both series will converge. Is there any questions on the limit direct comparison test and the limit comparison test? Okay. All right, let's move on to 9.5 then. This is the alternating series test. All right, let me grab my notes. Okay. They're 9.14 alternating series tests. Excuse me. let an be greater than 0. The alternating series test. The alternating series. So this piece right here is what makes it alternate. This is just some sequence, right? So some alternating series, and so these types will converge under these conditions. When these two conditions are met. So number one, the limit as n approaches infinity of an is equal to 0. Number two, it must be decreasing. In other words, an plus 1 must be less than an. This is for all n. Okay. So all we have to do is check if it meets these two conditions, then we can say that yes, that alternating series converges conditionally. Okay. So example 1, let's practice doing that. Determine the convergence or divergence of the following. All right. So first thing, number 1, the limit is the limit of an equal to 0. Well, let's find out. The limit of an will be this guy. You can clearly see that it's 0, right? So check for number 1. Number 2, is it decreasing? So in order to do so, all we have to do is this. Is n bigger than n plus 1? Yes, right, of course. No, sorry, other way. Therefore, this guy is bigger than this guy. So yeah, an plus 1 is less than an for all n. It's not going to change, right? This series converges We're going to say conditionally because it converges by those conditions. Because technically, if it wasn't alternating, if you only had this piece, you see how this would be a divergent P series, right? So it only converges because it's alternating and it meets these conditions. All right. Example, let's do another one here. Okay. Sorry. It's 1/3 to the n. Okay, so it is alternating. So all we got to do is check the conditions. So number one is the limit of an as n approaches infinity equal to 0. Well, the limit of 1/3 to the n is equal to 0, right? So that checks out. Great. Number two is an plus 1 less than an. In other words, is it decreasing for all n or at all times, right? So look at the series. It's always easy to build it off the reciprocal. So we know this guy is smaller than this guy. If I take the reciprocal, I know that this is bigger than this. So yes, the series, this alternating series, converges conditionally. Is there any questions about this example, these two examples? Okay. Well, let's move on to absolute convergence then. That's more important because we need to know if it converges absolutely, and but not only that, If it doesn't, then we start checking for conditional. All right, this is usually the second step. I guess I could fit it on here, I think. So theorem 9.16. One second. Okay. So if the series of the absolute value of a sub n converges, then the series of the original also converges. So basically what you're going to do is take an absolute value of the whole thing, and look at the AN part without the alternating piece. Okay, so get some more details here. There's some definitions of absolute and conditional convergence. The series of a sub n is absolutely convergent when the series a sub n converges. That's the value of a sub n. So this is absolutely convergent if this is convergent. Number 2, the series of a sub n is conditionally convergent when the original, basically when the alternating part converges, but the absolute diverges. Okay. Okay, so let's do an example where we check for absolute and then check if it doesn't converge absolutely, we then check for conditional convergence. So here's example 4. Determine whether the series converges absolutely or conditionally. If it diverges. All right, so here it is. So the absolute value of a sub n is equal to 1 over 5 to the n, right? You just take the absolute value of this guy. So there's my a sub n. So the series of the absolute value of a sub n is equal to the series of 1 over 5 to the n which is geometric. So since r is equal to 1/5, which is less than 1 by the geometric requirements, right? For series, geometric series. Since r is less than 1, r being the 1/5, then the series converges absolutely. Sorry, the original. Let me fix this better. Since this is less than 1, this converges. So this will be better. Thus, the original converges absolutely. Are there any questions about what we did here? Okay. Okay. So now let's do one where it does not absolutely converge, but it conditionally converges. Determine whether the series is absolutely convergent conditionally convergent or divergent. Okay, one moment, please. Okay, here it is. Sorry, I couldn't find it for a second. So it has the alternating piece, which is why whenever you have the alternating piece, is the reason why we keep asking about absolute convergence and conditional. So if you didn't have this piece, we would just treat it like we normally do, like the other tests. Okay. So absolute value of a sub n is equal to okay. Yeah, that's right. So we'll examine this guy and see if this converges. But you can kind of already tell that we can compare this to a p-series, and no, it won't. It won't converge, but this show our work. Okay. Right, so we will examine this one here and treat it like it's just a regular series, right? So we're going to use the direct comparison test. So a sub n is equal to this guy. B sub n is equal to 1 over n. So that's the one I'm going to choose. And you can see that this is smaller, right? So since a sub n is less than b sub n, and hold up. actually, comparison will not work because this needs to be smaller if it diverges. And this is we should be able to tell by looking at it, divergent P series. So we will use limit comparison instead, because if we get a limit of 1, then they will both do the same thing. In other words, they will both converge, right? Okay, so here we go. Then we have an over bn is equal to the limit which would then give us what? So since limit of an over bn is equal to 1, then actually this phrase is better. And bn diverges, then both diverge. Okay. But that doesn't tell us anything about. I should probably phrase this a little better. So if this was the question, then yes, we would be able to say this. But that's not the question. The question is this one, the alternating piece. Then, oh shit, I already have that up there. Then the series, let's talk about the original now. Is not absolutely convergent. One moment. Sorry. So since it's not absolutely convergent, this is where we decide, is it conditionally convergent? Okay. So number one, is the limit of a sub n equal to 0? Is the limit of a sub n being 1 over n plus 2? Yes. Number two, is it decreasing? Well, Yeah, it looks like it. This guy is bigger than this guy. This guy is clearly bigger than this guy. A sub n plus 1 is less than an for all n. Okay. So the original question, this tells us that the series -1 to the n plus 1 times 1 over n plus 2 is conditionally convergent, but not absolutely convergent. So that's what you got to do. So if it turns out it's absolutely convergent, we're done. Just stop. But if it's not, you still got to check the conditional. If both of those fail, then you say divergent. So it's a little more complicated when you have an alternating series piece. Okay. I guess we're out of time now. You guys have any questions about alternating series tests, direct comparison test, or limit comparison test? All right, guys. I guess go. I'm gonna check the due dates. These should still be open for a while. But I do read over the sequences series and then start getting into the different tests we've talked about if you haven't already. And maybe you can bring some questions on Tuesday, okay? If not, we're gonna keep on going through chapter 9. So please bring questions if you're stumped, because this chapter is a little tough for some people. So let me know. All right, guys, we'll stop here and I'll see you Tuesday.